Salam sejahtera and hi, my name is Lim Thian Mee. Today, I would like to present my Bachelor degree project 1. The title of my project is Synthesis and Optical and Semiconductor Characterizations on Molybdenum Diselenide MOSC2 thin films. I am under supervisor of Professor T.S. Dr. Johnson Anand. In this slide, this is about the thesis slide. There are 5 contents that I will present, which are Chapter 1 Introductions, that includes background, problem statement, research objective, and scope of research. Chapter 2 Literature review. Chapter 3 Methodology, preliminary results, and Gantt chart of this project. Chapter 1 Introductions. Firstly, the breakdown of this project. Lacking of natural resources, we have to depend on solar energy, and solar energy uses solar panel. This existing solar panel material is not very good, so we have to look for a new material and finding innovative materials with optimal properties for electrochemical energy conversions. Amongst the many other transitions, metal chalcogenase and extrude, which as referred to sulfur, selenium, and tellurium, are semiconductors that can be used as an efficient photovoltaic material. Hence, an exploration of minimum cost and air-abundant absorber materials of metal chalcogenase for high-efficiency solar cells is very important and popular. So, to prepare the transition metal of thin films, whether suitable or not, we're using a technique called electrodeposition, a well-known chemical technique. Electrodeposition is a thin film and or powder preparation process that uses an external current source to perform reductions or oxidation reactions. Thin films are thin layers of deposited material on a substance with thicknesses ranging from 10 of nanometer to 1 micrometer with bulk characteristics that differ. Thin film characteristics generally differ greatly from bulk materials because of surface and interface effects, which can influence behavioral patterns. Furthermore, solar panels are an optoelectronic device that is used and is becoming increasingly important in today's industry as a source of energy in everyday life consumption. For example, solar-powered water heating systems are the most well-known applications of solar-based energy gathering outside of horticulture. Next is the problem statement. With the performance limiting factors of their photoabsorbers, increase the concerns together with suggestions from this study for further improvement. Solar's energy has been prevented from becoming a more widely used energy source due to the problems such as its high cost and inconsistent availability. Since silicon is widely used materials, but it is still a costly material in pure silicon wafers, with miscompressed alignment and design throughout the production process. In order to compete with other photovoltaic technologies, silicon material conversion efficiency is only 12 to 14%. This part is research objective. There are 3 objectives of this research. First is to synthesize stoichiometric molybdenum diselenide thin films by using electrodepositions. Second is to analyze the optical characterizations of molybdenum diselenide thin films by using UV visible near-infrared spectrophotometer. And last one is to determine semiconductor parameter of molybdenum diselenide thin films for photoelectrochemical solar cells by using more scopely probe. The scope of this research is the properties of molybdenum diselenide thin films for use in photochemical solar cells. The synthesis of thin film of molybdenum diselenide will be done in chemical vapor deposition technique from high purity materials. X-ray reflections to determine structural properties of molybdenum diselenide thin films. Then, scanning electron microscope to examine the morphological properties of molybdenum diselenide thin films. And also, optical characterizations analysis by UV visible near-infrared spectrophotometer for the bandgap nature of molybdenum diselenide thin films. Lastly, the semiconductor parameters of molybdenum diselenide thin films are derived from the more scopely probe. Here, come to Chapter 2 literature review, starting with transition metal chalcogenase. There are semiconductors with a layer structure. Transition metal chalcogenase has been the target of several studies for their thin film characteristic. This is mostly due to the fact that many applications require the thin layers of them on substrates. There are also a type of semiconducting material that may be used as a photovoltaic material. Next is the molybdenum diselenide MOSC2. It is made up of series layers that are weakly coupled, with a MO atom layer connected between two Se layers. MoSe2 is very anisotropic and has unique structural features as a result of its structure. It is also a perfect choice for photoelectrochemical solar cells and photocatalysis due to its tunable bandgap. Thin film. A thin film is made of a thin layer of material that are ranging in thickness from a few nanometers to a few micrometers. Many new fields of research in physics and chemistry solid-state has been advanced as a result of thin film research, which is based on characteristics that are specific to the thickness, geometry, and fringe structures. Microelectronic device, photoconductors, infrared detector, solar cells, polar regions, superconducting films, anti-corrosive, and ornamental coatings are a few examples of the applications created by thin film. Thin film growth. This figure represents the typical material atom deposition thin film growth process on a substrate. A random nucleation process are for thin film to form. It is used to start the nucleation and growth stages of all thin film material. Another technique of tailor-made materials is represented by the process of hydrogenated amorphous silicon films to be used in photovoltaic cells. By changing the optical bandgap from 1 electron volt to a now 2 electron volts and lowering the ranging bond state density in the bandgap, hydrogenation allows doping of a N and P in amorphous silicon. Next part is growth modes of thin film. The thin film growth is followed by nucleation process. The classifications of this growth of thin films are divided into three modes, as shown in the slide, which are layer by layer growth, which is Frank van der Merwe FN, iron growth, Roman Weber VW, and layer plus island growth, Strengin Krestanov SK, respectively. Here show the cyclic voltammetric CV. The operation mechanism scans of electric potentials before approaching the final potentials. They reverses directions and scan the initial potentials again. It used to investigate redox processes and determine reactions product stability. The potentials of working electrons is continually changed throughout time, while the current produced by redox events is measured in its potential strip technique. Next, come to thin film depositions method. Based on one research by Whiting and Cato in 2020, physical vapor depositions (PVD) and chemical vapor deposition (CVD) are the two types of thin film depositions that are commonly used. When comparing physical and chemical deposition techniques, chemical deposition methods are preferable. Although physical deposition technique can produce high-quality films, however, scaling them is difficult. The figure that shows is electrodeposition setup. The use of these methods is well suited to the large area photovoltaic industry, and it is benefit in the mass production of copper indium gallium selenide solar modules. Chemical vapor deposition (CVD) is suitable technique to produce thin film. The figure shows aspects of CVD process. This technique allows the deposition of variety of structures, including metal alloys and compound semiconductors, with high purity and doping stoichiometric films control due to its versatility in working with a wide length of reactants and precursors. X-ray refractions (SRD). The SRD pattern obtained helps in the identification of different crystalline phases as well as the detailed analysis of their internal structural characteristics. X-ray refractions is a method for identifying and analyzing atom locations, arrangement in every unit of cells, and atomic plane spacing. Figure shows X-ray refractions technique. Scanning electron microscope (SEM). Scanning electron microscope (SEM) are a useful tool for analyzing and photographing a variety of properties of materials, including structural, topography, light emissions, and compositions. Figure shows components of scanning electron microscope. Scanning electron microscopy (SEM) based energy diffusive X-ray spectroscopic (EDS). The compositions of the thin film deposits can be determined by EDS analysis. This figure shows EDS results on cadmium selenide thin film. Optical properties by ultraviolet visible near-infrared spectrophotometer. The bandgap energy and optical properties of thin films were investigated using UV visible near-infrared spectrophotometer. Research by N.R. Powder and Y. Yan in 2014 found that in lilac bandgap semiconductors, absorbent layers as thin as a few micrometers are sufficient, and material qualities can be relatively poor. As a result, solar cells made of thin films with a direct bandgap materials attain the lowest cost. Shown in the figure, this is band diagram of semiconductor. For figure A is direct bandgap, and figure B is indirect bandgap. Photoelectrochemical studies. The semiconductor parameter like as dropping density, band bending, valence band edge, and others can be used to determine the photoelectrochemical solar cells factor of a semiconductor compound by using the Morse-Crooky probe. The inverse of square of capacitive versus the applied potentials to thin film is brought to tabulate potentials capacitive behavior data. Sarija and Anand in 2018 investigates the thin films of nickel sulfur selenide by plotting the Morse-Crooky probe at different deposition times. It shows in figure and its corresponding fat band potentials of the thin films from the Morse-Crooky probes in the table. These Morse-Crooky probes have a negative slope, highlighting that the depositions of films have p-type conductivity. Lastly, the summary of research gap of this project. Therefore, there are some summaries they can conclude from this research gap are: molybdenum diselenide MOSE2 thin films can be prepared by using cyclic water program reductions potentials. Second, optical analysis of molybdenum diselenide MOSE2 thin films can be studied by using UV visible near-infrared spectrophotometer. And the last one is semiconductor parameter can be determined from a Morse-Crooky probe. Here, come to chapter 3, methodology. This is the flowchart of my project. Firstly, starting by substrate preparations. Then, to synthesize thin film, electrolyte and electrodepositions were used. This figure is the cyclic voltammetric and electrodepositions experimental setup. Next, characterizations of thin film by thickness measurement which using width gain method. The reference in width before and after depositions were interspersed into equations as shown to determine the film thickness. Structural study with using X-ray diffractions. These machines will be used to confirm the structural characterizations and crystallography nature of thin films. Then, followed by surface morphology studies using scanning electron microscope. It will determine their grain or molecular structures by analyzing their surface morphology. Energy deposit X-ray spectroscopic EADS based on SDN had also applied in the research to study the thin film compositions and the stoichiometry of MOSE2 thin film. After that, optical study by using UV visible near-infrared spectrophotometer and also semiconductor parameter studies with Morse-Crooky probe, which two are the main characterizations tool of this project. A spectrophotometer is shown in the slide. The optical bandgap of thin film is calculated for transmission and reflection according to equations as shown. For semiconductor parameter are determined using the Morse-Crooky probe. Other semiconducting parameters such as semiconductor type, which are N-type or P-type, width of the depletion layer W, band bending VB, conduction band density of state NC, energy gap EG, and Fermi level of the semiconductor below conduction band can be determined using equations as shown. Next, for the preliminary results, molybdenum chalcogenase MOSE2, which is expected to synthesize by using an electrodeposition process. Second, optical studies will be used UV visible near-infrared spectrophotometer to study the optical properties. Third, the optical bandgap energy for the thin films that has been produced may be expected to measure between 1.2 electron volts to 1.5 electron volts. The last one is semiconductor parameter will be studied based on the Morse-Crooky probe. Here, we have a Gantt chart of my PSN1 semester 6, March 2022. Based on this Gantt chart, this shows all my tasks that I have done for every week. I spent 14 weeks to do my project from week 1 March until week 14 June. Starting from sessions of PSN1 titled PSN1 Briefing and up to the presentation slides and recorded video submissions. That's all for me. Thank you.